Somewhere on Earth, right now, there is a phone call that has been connected for almost 50 years. It has survived 11 presidents, the rise of the internet, and the death of most of the engineers who dialed it. The device on the other end is 25 billion kilometers away. Probably think the hard part is the distance. It isn't. Distance is just geometry. The real problem, the thing that should make this call impossible, is what distance does to a signal. Once you understand it, you will never take a phone bar for granted again. This is case file number 4, and it's a question file. Tonight, how weak Voyager's whisper really is, and the trick that lets us hear it anyway. The building-sized ears NASA built on 3 continents. The day in 2023 when NASA lost a Voyager and had to scream into interstellar space to get it back. And the countdown to the day this call drops forever. By the end, you'll know exactly how humanity keeps a phone line open across the solar system, and why the whole thing hangs by a thread thinner than you'd believe. Pick up the receiver. Act 1. The Whisper. Voyager 1 talks to Earth with a radio transmitter that puts out about 20 watts. 20. The bulb in your refrigerator uses more. And radio waves obey a brutal law. As they travel, they spread. Think about sunlight. Up close to our star, it is blinding, a furnace filling the sky. But travel outward, and that same light spreads over a bigger and bigger sphere. By Neptune, the sun is just a brilliant star in a black sky. Same energy, stretched over a surface so vast that every single point receives almost nothing. That law is called the inverse square law, and it never forgives. Run the numbers for Voyager, and they stop feeling like engineering and start feeling like a joke. By the time those 20 watts reach Earth, the signal arriving at our antennas is around a billionth of a watt. All of our giant dishes, together, have collected less total energy from Voyager in 50 years than a snowflake carries when it lands. NASA even built a clock for this problem, the Deep Space Atomic Clock, stable to 1 second in 10 million years. And yet the battery in an ordinary wristwatch is billions of times more powerful than the signal those clocks help capture every single day. That's the whisper. Now here's the part that makes it genuinely hard. The whisper has competition. This is what the radio universe sounds like. Every star hisses. Jupiter crackles. Our own galaxy hums across the entire dial. And Earth is the loudest of all. Every phone, every router, every radar, screaming at once. Listening for Voyager means picking one faint whisper out of the roar of an entire glowing planet. So how is this possible at all? 3 tricks. Trick 1. Agree on the exact spot on the dial. Voyager transmits on precisely known frequencies, in a band kept quiet by international law. Like tuning an old radio to one exact station, NASA doesn't search for Voyager. It knows, to the hertz, where the whisper will be. Trick 2. Cool the listener. The amplifiers at the heart of NASA's antennas are chilled to just a few degrees above absolute zero, colder than interstellar space itself. Why? Because warm electronics generate their own noise. To hear the quietest whisper in the solar system, the ear itself must be more silent than the void the whisper crossed. And trick 3. Know exactly when. Atomic clocks, accurate to a second in millions of years, timestamp every fragment of the signal, letting computers stack hours of whisper on top of itself until it rises out of the noise. Frequency, cold, and time. That's the whole magic. And it almost doesn't matter, because catching the whisper is only half the problem. First, you need ears. Giant ones. There's a wrinkle even the tuning trick can't escape. The station drifts. Voyager is racing away at 17 kilometers a second, and Earth is spinning and orbiting underneath the call, so the signal's frequency slides constantly, the same effect that bends an ambulance siren as it passes you. NASA's receivers don't just tune to a frequency. They chase one, sliding along the dial in real time, predicted to the hertz by computers that model both ends of the call. And spare a thought for Voyager's half of the problem. Its dish is 3.7 meters wide, and to keep this call alive it must point at Earth, a target it cannot see, to within a fraction of a degree, while tumbling through interstellar space on thrusters from the 70s. Every day, quietly, it does. The most impressive antenna pointing in history is being done by the oldest hardware in history. One more layer of armor, error correction. At these power levels, bits arrive mangled. So Voyager doesn't just send its data, it sends its data wrapped in mathematics, redundant patterns that let Earth reconstruct what static destroyed. A huge share of every transmission is not the message. It's protection for the message. Even Voyager's whisper wears a spacesuit. Act 2. The Ears. Meet the Deep Space Network. 3 antenna complexes, placed almost exactly 120 degrees apart around the planet. Goldstone, in the California desert. Madrid, in Spain. Canberra, in Australia. Why those spots? Rotate the Earth in your head. No matter which way the planet turns, at least one complex is always facing Voyager. The call never has to wait for sunrise. The crown jewels are the 70-meter dishes, antennas the size of a football stadium's bowl, weighing thousands of tons, yet able to point at a spot in the sky with the precision of a sniper. When even they aren't enough, NASA gangs multiple dishes together, combining their signals into one giant virtual ear. They did exactly that in 1989, adding an entire radio observatory just to catch Voyager 2's photos of Neptune. And what does all that engineering buy us? A data rate of about 160 bits per second. Your home internet is millions of times faster. A single photo from your phone would take Voyager weeks to send. This is the real texture of deep space communication, not a torrent, a drip. Every bit paid for with a stadium-sized dish and a frozen amplifier. Then there's the delay. A command sent to Voyager 1 travels at the speed of light and still takes almost a full day to arrive. The reply takes another day. Every conversation is a 45-hour round trip. You cannot joystick this spacecraft. You compose commands like letters, triple-check them, and mail them into the dark, knowing that if you made a mistake, you won't find out until the day after tomorrow. Picture one full day of the call. Morning over Australia. Canberra's dishes hold the line. As Earth turns and Voyager sets below Canberra's horizon, Madrid rises to catch it, and hours later hands it west to Goldstone in the California desert. The call follows the darkness around the planet, passed from continent to continent like a torch that hasn't been dropped in 50 years. And here's the strain nobody sees. Those same dishes serve more than 40 other missions. Rovers on Mars, telescopes at gravity's balance points, probes around Jupiter. Every one of them needs antenna time, and there are only so many giant ears on Earth. Deep space communication isn't just an engineering problem anymore. It's rush hour, every hour, on a network built when there were 3 cars on the road. Quick pause. If this case file is answering questions you didn't know you had, that's exactly what this channel does. Subscribe, because case file number 5 is already being written. Now, back to the call, because in 2023, it dropped. Act 3. The Shout. To understand what went wrong, you need one more fact. Voyager 2 flies below the plane of the solar system, so far south in Earth's sky that only one dish on this planet can send commands to it. Deep Space Station 43, the 70-meter giant in Canberra, Australia. One dish, one spacecraft, no backup. NASA knows how dangerous that is. In 2020, DSS-43 had to shut down for 11 months of upgrades, and for most of that time, Voyager 2 flew on in radio silence, able to whisper home through the listening antennas, but unable to hear a single word from us. A call on hold for nearly a year. When the dish came back online, the first test command went out, and Voyager 2 answered. The line had held. A routine batch of commands went up to Voyager 2, and buried inside it was a mistake. The kind of mistake that, on a 45-hour phone line, you discover far too late. The command tilted the spacecraft's antenna just 2 degrees away from Earth. 2 degrees. On your desk, that's nothing. Across 20 billion kilometers, it meant the phone slipped off the ear. The Deep Space Network aimed at Voyager 2 and heard nothing at all. Engineers searched the noise for any trace of the spacecraft, and eventually, buried deep in the static, they found it, a heartbeat. The carrier tone, impossibly faint, proof the spacecraft was alive and still transmitting, at an Earth that was no longer in front of its antenna. There was a safety net. Twice a year, Voyager 2 automatically resets its antenna toward Earth using its sun and star trackers. But the next reset was months away, and nobody wanted to spend months hoping. So NASA chose the other option, the loud one. If the spacecraft's ear is pointed slightly away from you, you shout. Shouting wasn't risk-free either. Aim wrong, time it wrong, or garble the command, and you've spent your best chance teaching a deaf spacecraft nothing. The team modeled where that 2-degree tilt had left the antenna's fringes, calculated exactly how much power it would take to punch a readable command through the very edge of Voyager's hearing, and rehearsed the message like a moon landing. They would get, in effect, one clean shout per attempt, with a 2-day wait to learn if it worked. On August 1st, 2023, DSS-43 turned its full transmitter power toward Voyager 2's position and blasted the command to repoint, aimed not at where the antenna should be, but at the sliver of sensitivity left at its edge. The signal crossed 19.5 light hours of space. Then everyone waited 37 hours for an answer. Think about that silence in the control room. A day and a half, listening. And then, on the screens, data. Voyager 2 had heard the shout, swung its antenna back, and picked the phone back up, as if nothing had happened. NASA called it the interstellar shout, and it remains one of the loudest, deliberate transmissions humanity has ever aimed at the stars. We didn't just call across the solar system. We yelled, and a machine from 1977 heard us. Act 4. Every phone call ends. You know from Casefile number 1 that Voyager's plutonium heart loses about 4 watts of power every year. Instruments are being switched off one by one to keep the transmitter alive, because the transmitter is the mission now. The science matters, but the call itself is the miracle worth protecting. Sometime in the early 2030s, engineers expect the power to drop below what the radio needs. Somewhere on Earth, an operator will send a command knowing there may be no reply. And the Deep Space Network, which has more spacecraft to serve every year and only so many giant dishes, will quietly reassign the hours it spent on Voyager to younger missions. The longest phone call in history will end not with a bang, but with a schedule change. But the story of impossible calls is just beginning. NASA is already testing the next telephone, lasers. In 2023, an experiment called Deep Space Optical Communications fired a laser from far beyond the moon's distance and streamed data to Earth hundreds of times faster than radio, including, because engineers are human, a video of a cat chasing a laser pointer. The next Voyager won't whisper in radio. It will flash in light. And don't forget who's actually on this call. Not NASA, the abstraction. People. Operators working night shifts in Canberra and Madrid and the Mojave, checking a carrier tone from a machine older than they are. Engineers who inherited Voyager from their teachers, reading binders written by hands that are gone. Someone is listening right now, tonight, while you watch this. The phone line is technology. Keeping it open, for half a century, is devotion. And maybe that's the real answer to this Casefiles question. How do you keep a phone line open across 25 billion kilometers? With 3 tricks, 3 continents of steel, frozen amplifiers, atomic clocks, one very loud shout, and a species that, once it hears a voice in the dark, absolutely refuses to hang up first. One day, within most of our lifetimes, the line will finally go quiet, and the dish in Canberra will tilt toward a spacecraft that can no longer answer. So here's tonight's question for the comments, and I genuinely want to know. If you could write the very last command humanity sends to Voyager, the final words of a 50-year phone call, what would you say? Subscribe for case file number 5. Keep the line open.